Welcome. My name is Chuck Ridgway. I'm the Advanced Technology Manager here at Horner. And thanks again for joining us for another one of our live streams. Today, our program is all about math. The subject that many of us as engineers probably did really well in school, or maybe not so much. It all depends, I guess. Joining me today is Casey Gardner. How's it going, Casey?
Hey, not too bad.
Good. Hey, did you ace
Somewhat
all the
good
math?
math.
Did you ace all the math classes in college?
I don't know about ace them. We definitely took plenty of them.
Yeah, that's true.
Oh goodness.
With engineering, it always ends up that way. So anyway,
Yeah.
today it's all about math. We're going to talk about integer math, floating point math, all kinds of, plain old arithmetic functions, more significant functions, trigonometric, logarithmic functions, all that kind of good stuff. So in the applications that you've worked on lately, anything that kind of stands out in terms of the type of math that you've been doing?
I think the most common ones are definitely your basic ones, your add and subtract, multiply, divide, especially a lot of conversions from different types of whether it's values or even converting temperature or weight values, that kind of things
Yeah,
as well.
engineering units, that sort of thing, right?
Absolutely. But then, I mean, especially our expression tool makes a lot of that pretty easy for sure.
Yeah, it really does. And then, even though it's only loosely related to math, the scaling block also is really helpful when you're just doing simple conversion from analog inputs that are, coming in from 0 to 32,000 counts over to, milliamps or, more realistically pressure and that sort of thing.
Yeah, absolutely.
Okay, good deal. Well, let's go ahead and get started. Let's take a look. And again, we're talking math today. And for the most part, what we're going to be doing today, it's all going to be about demonstration for the most part. So we're going to be showing you, you know, what the math functions look like, leading you through all the different programming languages and how they vary somewhat in doing math, that sort of thing. So I'm starting out here with just plain old advanced ladder, register based. So for those of you who are still using advanced ladder that's register based, and it's frankly still our most popular option out there, if you remember correctly, we have to assign, every time we assign a variable, we also have to assign its register location. So, but let's get started and take a look at the math. So in the math discussion, what we're really looking at here are kind of the base functions, add, subtract, multiply, divide. Those are fairly straightforward. Casey mentioned that we do have a expression function that we're going to go through that is very handy, allowing you to, take several functions that would normally be cascaded together and doing everything in a single expression block. But we're not going to stop at the basic math. We've also got advanced math, which includes logarithmic and trigonometric functions, as well as scaling, which is very, very useful. And then whenever you are doing math that involves maybe a mix of different variable types from integer to floating point or whatever the case may be, then there's also what we call conversion operations as well, for converting from one type of variable to another. So we're going to cover all of that. And again, we're starting out with advanced ladder register based, but we're going to go through the other languages as well. And as a teaser, I'm also going to show you a couple of ways of actually using logarithmic and trigonometric functions in like real world type applications. So you probably thought that wasn't even possible, right? Okay, let's go ahead and get started. So once again, I'm just in the advanced ladder with register-based advanced ladder here. Anytime that we are doing any kind of math or anything else that involves function blocks, even if there really isn't any Boolean logic involved in the calculations, we still need to have a contact at the beginning of the rung. That's still a requirement. So we start off with our always on contact, and let's just start out really simple. Let's just throw an add block on here. Okay, so the first thing that you do once you go in to configure a math block of any kind, regardless of how
Hey, Chuck,
complex. Yeah,
real quick, it looks like we've still got the math functions overlay on.
well, that would be probably, A good point, Casey. Thank you for pointing that out.
No problem.
How about that? Let's dig into there instead. Okay, so not to back up too far, but again, we're looking at our math operations. We're looking at our advanced math operations, which we'll be looking at next, and our conversion operations. Okay, so I've dropped an add block on the screen here. And the first thing we have to do is we really need to take a look at what type of variables we're talking about here that we want to do the math on. So it's very important to note that regardless of the language, regardless of the math block, all the functions need to match. So if you're doing a calculation on integers, then all the operands as well as the result all need to be integers. If you're going to be doing math on floating point variables, all the variables, inputs and outputs, have to be floating point. So that's very important to note. Now, before we dive in any further here, I'll just review the different options. Now, with integer math, all of our values have to be plus or minus 32,767. We've also got an unsigned integer, where the values are going to be positive only from 0 to 65,535. We have double integer values that are 32 bits wide, so they take up 2 consecutive registers in the register-based math, and those are positive and negative as well. Unsigned double integers, again, 0 on up to very large numbers that are 32 bits wide. And then we've got real, which are 32-bit floating point values. And then long real, which is a relatively new addition to the Horner product line, and that is 64-bit floating point values. Now, all of our products, all of our modern products can handle all of these data types for the basic arithmetic functions. So add, subtracts, etc., those can all be used for all these different types. Now, some of the advanced types, like the logarithmic or the trigonometric, those only are real and long real only. Okay, so let's see. Looks like we've got some technical issues going on here. Are you seeing that, Casey? Or do you think it looks okay on our end?
I think it looks okay on our
okay,
end.
Very good, very good. So once again, Casey's taking care of me, making sure that that hopefully those of you out there can see what needs to happen. All right, so we're going to start out with just a simple integer math function here. So I'm going to start by just adding a couple variables together. So again, with register-based ladder, you have to have all the types match. So we're going to start with integer variables. I'll pull them off the list here. So I've just got pre-configured a couple variables, variable 1, variable 2. All right, I've also configured a variable called sum. All right, we'll configure that. And there we go. So simple math block, add two values together, create a sum. You know, what could be simpler, right? We're going to get a lot more advanced than that. Well, let's say that we want to build upon that and we're going to create an average. Well, to do that, we're going to add the values together and then we need to divide. So one option we do have is to cascade functions together. So I'm going to go ahead and add a divide function here. And we'll start out with our sum because those are the two values we just added. Okay. And then we're going to divide that by the number of samples. And again, all these are integers. They all have to match. And then our answer is going to be a variable called average. There we go.
One quick question.
Sure.
Coming in, Chuck.
Yep.
We got Nigel Bradbury, and he's asking, is there consideration of long double integer for precision instruments?
We don't have that in there yet. That's a good suggestion. So that's something I'll talk to our engineering team about. I'm assuming those must be 64-bit integers. At this stage, we have 16-bit integers and 32-bit integers, 32-bit floating point, and 64-bit floating point. But that's a interesting suggestion there. Okay, thanks, Casey.
I can't remember if it's coming in Service Pack 4 or not, but I'll double check.
Okay, that's good to know. Okay, so this is how we just cascade together function blocks. Now, what happens, for instance, if we're doing integer math and we have an overflow? All right, so we know that every value here cannot exceed, for integer math, 32,767. All right, well, if our values are exceeded, if that integer value is exceeded, what happens is this function block will not pass power. So in that scenario, this function block will not pass power. Same thing for a divide block. If we're dividing by a variable and it turns out to be 0, so we're going to have a divide by 0 error here, well, that's a problem as well. So one option you do always have to try and flag a issue with a function block is you can put, with a math block, for instance, you can go ahead and put a coil at the end of the rung if you like that says math okay. And then if you ever have a problem with one of your math blocks where they, have an overflow or they have an issue with a divide by 0, well, in that scenario, this has been flagged because this bit will be off. Okay, so this is just basic cascade together math type functions, simple arithmetic stuff. Let's go ahead and now let's do the same calculation, but this time let's do it in an expression. And remember, we're doing this still in advanced ladder, this register based. So I'll be going through the other languages or the other options control wise coming right up here. Okay, so I've created a new rung, and this time I'm going to use the math expression block. Okay, so in this scenario, again, we start out by determining do we want to do integer or not. In this scenario, we can just go ahead and type in the equation. And for instance, we have the ability to do something like this. Average, and I'm having to use variable names here, equals variable 1 plus variable 2. Now I'm going to want this to be executed in the proper order. So I'm going to go ahead and make sure I have parentheses in here, divided by samples. Okay, so this is now an option I have with the math expression block. Now, when I hit OK here, I'm going to get an error, and I'll explain why in a second. Expression must start with a memory reference. Okay, now this only applies to register-based advanced ladder. This does not apply to variable-based advanced ladder. So in the case of register-based ladder, you do have to start a math expression block with a memory reference. So I can't type in average for the result. I have to type in the memory reference. So in this case, average is R5. So I'll type in %R5. And I believe that's something that's on the list to be addressed, but currently that is a limitation. Okay, so that's the simple math expression block there.
I've got another question coming in, Chuck.
Sure.
This is from Peter and Zant.
Mm-hmm.
He's asking if the math is not good, in a case like a divide by 0, for example, that would happen. What would happen to the value of %R5 in your example? Would it remain on the last value, or would it be a random value?
One thing I do know is you can't necessarily trust the value. I believe it goes to its last value, but I'm not 100% sure of that. We'll double check and do a follow-up on that. But that's another reason why you'd want to use a kind of a math OK block, so that, or a coil here, so that you know that, oh, that's not on. I must have an overflow error or a divide by 0 error. And so therefore, I've got to I want to set my result here to some default value with another rung of logic. Okay, so that's a good follow-up question. I'll get with that. Okay, so this is the basic math functions. Again, we've done everything in integer math. We have to worry about overflows. We have to worry about divide by zeros, those sorts of things. But in the case of the advanced ladder, it's not going to pass power flow if any of those things happen. All right, now let's take a look at, just real quick anyway, staying with advanced ladder that's register-based, let's take a quick look at some of the advanced math functions here as well. Okay, so one of the differences here with these advanced functions, whether they're logarithmic or whether they are, trigonometric, like sines and cosines and the inverses and all those sorts of things, is these functions. Let's go ahead and take sine, for example. One thing you'll notice about these functions is they are real only. So either standard real, which is 32-bit real, or 64-bit real. Those are the only options you have. So we don't have integer equivalents of the advanced math functions, at least from the standpoint of the logarithmic and trigonometric stuff. So that's something to be aware of. Okay? Okay, so instead of diving further into, well, let's cover one more thing before we move on. Okay, so again, with the advanced math, you do have really only real type functions available. Let's take a look now at what happens if we're going to do a calculation, and let's say we have a mixture of different variable types. Let's say we have an integer and a real value that we want to average effectively. Okay? Well, one thing we have to make sure we handle is that we have to make sure all the variables are of the same type. And that's where these conversion operations come into play. Okay, conversion operations. So if I have, let's say I have an integer and a real value, I want to average those together through a calculation, I'm either going to have to use one of these conversion functions to convert one of my integer variables over to a real variable, or the other way around, if I want to do the math in the integer domain, I would need to use a real to integer function or conversion function to convert from a real value back to an integer. So don't forget about these conversion functions. They do allow you to effectively, do math on variables that are starting out as different types. You take the types that aren't matching, you convert them over to the matching type, and then you do your calculation. Because once you get down to the function block level, these all have to be the same type. Every variable on here has to be of the same type. Okay? All right, I'm going to go ahead and let's go ahead and load up a program here that is using advanced ladder with tags, or variable-based advanced ladder. Let me go ahead and arrange my screen a little bit here. All right. Okay, so just to refresh your memory for those who aren't as familiar, when you are programming your logic in advanced ladder with variables, or advanced ladder with tags, as it's sometimes called, instead of getting all your variable names handled by the IOName tool, we have this program variable window instead. Okay? All right. And let's take a look at the variables we've created here. All right, so I've created some variables here, and before we dive into the specifics of this particular example, let me show you this math expression block. So as you can see, with advanced ladder with variables, you don't have that restriction of having to have a memory location or something like that at the left side of the equation. Everything in here is all variable based, which is nice. Okay, so that makes it a lot simpler. Now, a couple of the other limitations I didn't really talk about before that I'll mention now. When you're using the math expression block, regardless of which programming language you're using for control, you are limited to 160 characters total. So that is something to be aware of. So if you've got a lot of really long variable names and a very complex algorithm, in theory, you could run out of space in your function of the 160 characters before you're done. But I think most of the time, you won't have to worry about that. It doesn't happen all that often. But anyway, with the math expression block, you don't have that limitation that we have with the advanced ladder register-based version. Okay, I'm going to go ahead now and show you an example. All right, so what I've done here is I've created a couple of examples showing that occasionally it's actually practical to use logarithmic and trigonometric functions in a real application. And let's go ahead and let me go ahead and show that to you now. So let's say that we have a application where we want to, we have a large object. I'm showing a tree here on the screen. That just gives you an idea what we're talking about here. But you've got a large object and you want to be able to measure the height of it, but there, isn't a real good practical way of doing that, using a sensor directly. You could use the tangent function as an example in combination with, say, an inclinometer, say that 10 times fast, as well as maybe a laser sensor that gives you a horizontal distance. So if you know the angle from the ground to the top of the object, and you know the horizontal distance from the measuring device to the base of the object, then using the tangent, you can go ahead and calculate the height. Okay, so that's an example. Let me go ahead and show you how we're programming that with advanced ladder with tags. Okay, so what we're doing here, and I'll double click here, effectively our calculation is that the height of the object is the horizontal distance times the tangent of the incline angle. Now, one thing that you need to be aware of is for all the trigonometric functions, the angle is always needs to be expressed in radians. Okay, so if you're using the tangent or the inverse tangent or sine or cosine or any of the others, you need to make sure that the angle is in radians. So in this example, what we have done is before this math expression block, we have done a degree to radian conversion function. So our angle that's on the screen has been converted to radians so that we can do our calculation properly. Okay? All right, so we do our, I selected the wrong type here. There we go. Okay, so we have a degree to radian conversion, and then we do a simple tangent conversion. Okay? And then if we take a look again at our application, if we adjust the angle, let's say it's a 70-degree angle instead of a 55-degree angle, obviously our tree is much taller, than if we've got our original 55-degree angle. Or if we get a lot closer to the tree, but keep the same angle, again, it's going to affect our height as well. Okay, so that's just an example of a simple application using a trigonometric function in this case to handle a calculation in our application. All right, now let's say that we want to do the same calculation, but we want to do it, let's say, in our IEC languages using structured text. I'm going to go ahead and open another program here, okay, that does the same math calculation, but this time using structured text. Okay, so structured text, for those of you who are IEC users, it's often a fantastic option for doing math functions. It's good for a lot of things, obviously. It's good for sorting. It's good for, string handling. It's good for math. There's a lot of things it's good for. Still some things I prefer ladder for sure, especially when it comes to machine sequencing and those sorts of things. But when it comes to math, string handling, etc., structured text is pretty awesome. Okay, so let's take a look at what we've got going here in structured text. Just like we just did in advanced ladder, we effectively need to convert our incline angle from degrees to radians. So we have the syntax here of the incline rads variable, so that's the incline angle in radians, is equal to, and then we do a degrees to radians function on the incline angle, which is a real function. Okay, so that gives us our incline in radians, and then in the next step, we do our object height calculation by taking object height, setting that equal to the horizontal distance times the tangent of our incline in radians. Okay, so that's an example of structured text to do math functions. Now, one of the nice things about, when you're using structured text, we've got this maths area here, okay? And if you're not sure about the syntax, you can always drag over any of these functions onto your desktop, onto your editing area, and it'll give it to you. So for instance, I'll drag the absolute value function over. Okay, let me create some space here. All right, sorry about that. There we go. create some open space. Okay, so there's the syntax for the absolute value function. Okay, so it's ABS. Inside of brackets, you have your variable that, as you can see here, it's telling you through the comment that can be any data type. So it doesn't have to be real. Whereas if we take a look at the log type, for instance, okay, that guy has to be real. So inside the parentheses, your variable is here, and it's got to be the real type. So again, that can be really handy if you're not sure what the actual syntax is. It's really handy in structured text. It'll just go ahead and give that to you. Okay? All right, so those are some fairly simple example there of using structured text to do the math. Now, just like in ladder, though, you do need to make sure that anytime you're doing a calculation, that all of your variables are the same type. So that's definitely a requirement that you need to be aware of still. Okay, I'm going to go ahead and delete this here. All right. Okay, now let me show you an example of maybe a simple math function that we might use a logarithmic function to go ahead and solve. So let me go back to my example here. And this time, let's take a look at our logarithmic function example. Okay, so in this scenario, what we're doing basically is we're using Newton's law of heating and cooling to solve for the heating time for taking an object that starts off at a certain temperature. We're going to put it into an oven that has an ambient temperature or a cooking temperature or a heating temperature, whatever we want to think of it, an oven temperature basically. And then we want to heat it up to a final temperature. So maybe we start out at, let's say, 40 degrees Fahrenheit. We want to finish up at 165 degrees Fahrenheit, and we want to know how long that's going to take depending on the oven temperature, and of course, depending on the material coefficient, because materials are different, of course. But this is an example of where we could use the natural log function. So at the top there, I've shown, again, Newton's law of heating and cooling that uses basically the natural log to make that happen. So you basically take 1 divided by your material coefficient, multiply the natural log of your oven temperature minus the final temperature of the material, divided by the oven temperature minus the initial temperature of the material, and then it basically solves for the heating time. So in this case, you can see that we're calculating 2.9 hours of heating time to take this particular material from an initial temperature of 40 to a final temperature of 165 if our oven temperature is at 375. So if we adjust the oven temperature, the calculation is going to adjust, and you can see that the heating time has gone down somewhat. Okay, so how would we do this sort of calculation as well? Let's go ahead and take a look. Okay, so let's go ahead and start with structured text since we're already here. All right, so this is my heating calculation, and you can see in structured text I can pretty much do it all in one fell swoop here. All right, so I've got my heating time variable equals -1 divided by my material constant, all right, times the natural log. Now in structured text, you have 2 different logs. You have a log base 10, and then you have your natural log. So they just happen to draw it as log, even though it is the natural log. Okay, but the log of, and then this is where we take our differential between our oven temperature and our final temperature, divided by our oven temperature minus the initial temperature. Once we make that calculation, we take the log of that, and we end up with the heating time. So again, that's an example using structured text of how to do that sort of calculation. Let's go ahead and take a look at, let's go all the way back, let's say, to advanced ladder and see how we would do that. Okay, so here's our logarithmic calculation. All right, we were able to write the whole thing out with the exception of the result. Again, and a limitation of advanced ladder, register-based, is that with the result, you have to put the memory location as opposed to the variable name. I think that's probably something that we could enhance, but that's currently the way it works today. Okay, so hopefully that'll give you an idea from a math function, advanced math function. Again, the key points are for basic math functions, you can use integer, double integer, floating point math. For the advanced math functions, those are floating point only. Regardless of the calculation, you need to make sure that all your variables are of the same data type. And if you have a divide by zero, or if you have an overflow, say in integer math, then the functions are not going to pass power. So it's probably a good idea to put a OK contact after the functions to make sure that your math function did actually calculate. Okay, last thing I want to cover here is I want to take a look at the scaling functions, because these can be really useful. So let me go ahead and, again, I'm in the register-based ladder. So I'm going to go under advanced math and select scale. And this is a very useful function. And let me scroll up a little bit here. This is a very useful function for taking analog inputs, for instance, and scaling them to engineering units. So I'm going to go ahead and create a new rung. Again, it would be illegal if I didn't put a contact here. That's just a rule that we have with our advanced ladder. Okay, an advanced ladder with tags. Okay, so I've got a scaling function. Now, one of the things there's a couple ways to handle scaling. One option that is realistic for a lot of engineering units is to do everything in integers. Okay, that is a realistic approach for certain engineering units. So as an example, let's say my input is coming from, go ahead and move this screen out of the way here. Let's say my input is coming from analog input number 1. All right, and let's say this is raw pressure. And again, I'm defining everything as I go here because I'm using advanced ladder with register based. And let's say its values are coming in from 0 to 32,000. And maybe that's 4 to 20 milliamps. We're at 4 milliamps, I'm going to have a value of 0, and at 20 milliamps, I'm going to have a value of 32,000 in my analog input register. But what I'm really after is I'm after, let's say, a pressure value. So let's say I'm going to pick just a general purpose register for that guy. Let's say I'm going to pick register 100, and I'm going to name it pressure PSI. All right. And let's say that for this particular pressure sensor, that my minimum pressure is 10 and my maximum pressure is 100. Okay, so I could use this scaling function and it would work perfectly well. The only negative here is that I'm taking a pretty high resolution analog input and I'm rounding everything off to the nearest pound per square inch. So that's probably not what I want to do. Well, another thing I can do, though, is because my numbers are small, I can add one or more implied decimal points. So maybe 10 will be represented by a couple extra zeros here, and 100 will be represented by a couple extra zeros here. So what I can show on the screen is 10.00 or 100.00. Now, I haven't converted those over to a floating point value, but what I have done is allowed for placing an implied decimal point on my screen when I display it on the screen. So as an example, let's go ahead and do that now. So I'm going to go ahead and pull up a screen here. Okay. And I'm just going to find a available screen just to illustrate this. I'll put a numeric object here on the screen. All right, I'm going to stick with integer math. I'm going to select from the list. Let's see, what did I call that? I think I called that pressure PSI. There we go. Now, when I display this, I'm going to go ahead and display this as a decimal value. Okay, and there's no sign involved. But I'm going to go ahead and put an implied decimal point in the display here. So let's say 3 digits to the left and 2 digits to the right. And then I'll put engineering units of PSI in there. I'll make the font a little bit bigger. Okay, I'll give it a legend for pressure. Put a little bit of a bigger font size there, and expand it so it isn't too small. There we go. All right, so anyway, so that gives an example of how all the scaling that we did stayed as integers, but yet we're displaying the value on the screen in engineering units, and we never converted from an integer to a real value. Okay, so that's one way to do it. And it doesn't work for everything either, because sometimes you could have potential overflow issues and those sorts of things. So let's go ahead and now do it the other way, where we actually convert the value over. So let me scroll up and I'll do another point this time. All right, so I'm going to go ahead and start a new rung here. All right. Now, let's say I'm starting with an integer, but I want to do the scaling in floating point. Well, the first thing I'm going to have to do is convert my analog input integer over to floating point. So I'm going to use the conversion function. Okay. And I will convert integer to real. All right, so this time let's do AI2. And we'll call that pressure 2 PSI, I'm sorry, raw. And let's convert that over to, I'll just pick a new value here. We'll call that pressure 2 PSI. Well, actually, it's still raw. It's just real. How about that? There we go. Pressure 2 real. That makes more sense. Okay, so I've created a new variable that just is the real equivalent of this integer number. And now I can go ahead and go back and do my scaling function. But this time when I do my scaling function, instead of doing it in the integer, with integer variables, I'll do it with real variables. So my input now is going to be pressure 2 real. All right. It still has a minimum of 0 to 32,000. Okay. But now my output, I can put that at, I'll just create a new one here called pressure 2 PSI. And again, let's say it's the same scenario, 10 to 100 pounds per square inch. And because I'm using real, these values won't be truncated as integers, and I'm good. Okay? So same scenario. Now if we go to put this guy on the screen, okay, I'm going to go ahead and copy this and paste, but I'm going to have to change some things here to make this work. First of all, this is a 32-bit variable that we're going to be dealing with. Okay, it's going to be not decimal, it's going to be floating point. And I need to select the proper variable here, which is pressure 2 PSI. And then I also want to select the proper number format here, which we will call, we're still going to want to display it in the same way. So 1.123.12. Go up a little further. Always takes me forever to find these. 123.12. There we go. And of course, we should probably change the legend, but I'll leave that alone for now. Okay, so what I showed you there was two ways of using the scaling block, just sticking with integer and using the real version of it. Okay, so I think that covers, for the most part, that covers what I wanted to cover today. Casey, anything I missed? Anything you can think of?
No math functions in particular. We might make a couple notes just for some of the users that might make things a little bit easier as they're doing things. So one function we have support for in our advanced ladder with tags specifically, starting with Service Pack 3, which is our most recent version, is our user-defined function blocks. So a lot of the math that you were doing, you could kind of simplify and save in a function block, and then all you'd have to do for future applications is just use those variables and enter in your values, and it'll output a value really easily. So that's kind of a nice feature we've added in.
Yeah, that's a great idea. And actually, frankly, for doing special algorithms and things, that's probably the way in which I've used user-defined function blocks the most, whether it's a math algorithm or a sorting algorithm or something else. So yeah, that's a really good suggestion.
Absolutely. And another math function that we have that we didn't necessarily go into detail is our PID functions, which Chuck actually has done a webinar last year. So if you want to take a look in our webinar section of our YouTube videos, there's a pretty good webinar that goes into more detail on the PID side, which is doing a bunch of math behind the scenes. So that's another advanced tool we've got.
Yeah, and the PID algorithm basically is integer based for the advanced ladder and advanced ladder with tags. And then you have your choice between an integer based one and a floating point based one for the IEC. Now, I will say this though, 99% of the time, an integer based PID is going to work perfectly fine. There's no huge advantage at all to having a floating point version of that. It's just, I think sometimes we get hung up on, floating point must be more exact. Well, not necessarily. So don't be too concerned about integer-based PID. They work really well. Okay.
Awesome. I
Great.
think we have a couple.
You have any questions?
We'll get back to. Just kind of one of the
Okay.
open-ended ones was regarding a scan time specifically for the expression block.
Sure.
I think Nate made a comment in, but I can try to see if engineering has a more exact value for him.
Okay, very good. Yeah, I mean, the expression block doesn't take any more time than the separate blocks do. If anything, it may save a little bit of time. Now, there is a difference in between the resources required to do floating point math versus integer math. So that is a factor. Now, unless you're really, really managing every millisecond or fraction of a millisecond, frankly, of your scan rate, that's probably not going to have a huge impact in most applications. Our products are pretty speedy, especially if you're talking about the XL series and the XL Plus 15-inch product. Those are pretty speedy, and even though there is a difference in terms of floating point execution time versus integer math execution time, it's not crazy unless all you're doing in the application is just a bunch of math. Okay, very good. Well, thanks again, Casey, for keeping me from hitting the iceberg too hard. I did forget to switch over to the computer, and if you weren't there, we would have been looking at a title screen for about 40 minutes. That wouldn't have been any fun. So I appreciate your help in that. All right. Well, we've got another live stream coming your way next week. We'll be announcing that in the next couple hours as to what that live stream will be topic-wise. So thanks for joining us. Again, if you have any questions, don't hesitate to email us. Also, don't hesitate to subscribe to our YouTube channel, and also check out our website at www.hornerautomation.com so that you can see all of our events that are upcoming, whether they're live streams or full-blown webinars. And again, we just really appreciate the time that you've spent. Everybody, stay safe out there, and we'll see you next week.